On a quiet October evening in 2019, the Catalina Sky Survey's automated telescope captures something unusual moving across the constellation Gemini. The object appears as nothing more than a faint smudge against the stellar background, barely distinguishable from the thousands of asteroids that populate the space between Mars and Jupiter. Yet within hours of its discovery, preliminary orbital calculations reveal something extraordinary. This visitor moves with a velocity that doesn't belong to any known asteroid or comet 17 kilometers per second, relative to the solar system's center of mass. Far too fast to have originated from within our cosmic neighborhood. The discovery team designates it 2I Borisov, the second confirmed interstellar object to pass through our solar system. Unlike its mysterious predecessor, 1I, Oumuamua, which resembled a tumbling metallic cigar, this newcomer behaves like a proper comet. As it approaches the Sun, solar radiation begins to warm its ancient nucleus, sublimating primordial ices that have remained frozen for millions of years. A delicate coma forms around the kilometer-wide core, followed by twin tails of gas and dust that stretch for hundreds of thousands of kilometers behind it. Across observatories worldwide, astronomers point their most sensitive instruments toward this wandering emissary from another star. The Hubble Space Telescope tracks its approach for months, measuring the subtle changes in brightness and colour as the comet awakens from its interstellar hibernation. Each spectrum reveals familiar molecules: water vapour, carbon monoxide, cyanogen and diatomic carbon, yet their abundances and isotopic signatures carry the unmistakable fingerprint of alien origins. The comet's nucleus appears reddish in colour photographs, similar to objects in the Kuiper belt that have been weathered by cosmic radiation over billions of years. Yet chemical analysis reveals subtle differences in composition that speak to an entirely foreign pedigree. The ratio of carbon monoxide to water exceeds anything observed in native solar system comets, suggesting formation conditions around a different star with a different temperature profile, different elemental abundances, different planetary dynamics. Radio telescopes detect faint emissions from the comet's coma as carbon monoxide molecules absorb and re-emit solar photons. The signal strength provides clues about gas production rates, nucleus rotation, and internal structure. Scientists calculate that 2I Borisov loses roughly 20 kilograms of material every second as it approaches perihelion. Not much by terrestrial standards, but enough to create those ethereal tails that stretch across the inner solar system like cosmic contrails. Ground-based observatories measure the comet's polarization properties, revealing details about the size, distribution and composition of dust grains expelled from its nucleus. These particles, microscopic fragments of another star's planetary formation process, drift slowly away from the comet under the gentle pressure of solar radiation. Some will eventually spiral into the Sun, while others might persist in heliocentric orbit for millions of years, indistinguishable from the zodiacal dust that already permeates interplanetary space. Deep photographic surveys attempt to detect any fragments or companion objects travelling alongside 2I Borisov. But the comet appears to journey alone through our solar system. Its nucleus shows no obvious signs of splitting or catastrophic disruption. Despite having endured eons of bombardment by cosmic rays, interstellar dust grains, and the occasional micrometeorite during its long passage between the stars, only took 4.5 billion years of wandering through the galaxy's most empty regions to arrive at our doorstep, carrying with it the geological memory of conditions that existed when our own solar system was still forming. Theoretical models attempt to trace 2I Borisov's trajectory backward through space and time, seeking clues about its stellar origin. The calculations prove challenging because the comet's motion has been influenced by gravitational interactions with countless stars during its interstellar journey. The most probable candidates include red dwarf systems within 50 light-years of our current galactic position, ancient, long-lived stars that might have ejected this wandering ice ball during the chaotic early phases of planetary formation. As 2I Borisov continues its hyperbolic trajectory past the Sun, one unsettling question emerges from months of careful observation. If astronomers can detect objects this size only when they venture close enough to develop visible Comet, how many similar visitors pass through the outer solar system unnoticed, invisible in the cold darkness beyond Neptune's orbit? Statistical models based on the discovery rate of interstellar objects suggest that dozens, perhaps hundreds of such wanderers traverse our solar system every year, most of them too small or too distant to register on existing sky surveys. The implications ripple through the astronomical community like slow-moving shockwaves. If interstellar visitors arrive this frequently, then Earth drifts through a cosmic ocean filled with debris from other stellar systems, fragments of worlds that never formed, remnants of planetary collisions, evaporated comet nuclei, and perhaps stranger objects whose compositions reflect entirely different pathways of cosmic evolution. Most pass by unnoticed, like ships in the night, carrying their alien chemistry through our local space and continuing toward whatever gravitational encounters await them in the galaxy's depths. The mathematics begin with deceptively simple equations, orbital mechanics, refined over centuries of celestial observation, describe how objects move under the influence of gravitational fields. When astronomers first calculate 2I Borisov's trajectory, the numbers reveal something profound about the nature of space itself. The comet's hyperbolic orbit carries an excess velocity that cannot be explained by gravitational interactions within our solar system. Its eccentricity exceeds unity, a mathematical signature that marks it as fundamentally foreign to our cosmic neighbourhood. In the quiet hours before dawn, graduate students at observatories worldwide perform the same calculations, double-checking their predecessors' work. The orbital elements paint a picture of vast distances and unimaginable timescales. Borisov approaches the Sun from the direction of the constellation Cassiopeia, suggesting an origin somewhere in that region of the galaxy. But somewhere encompasses hundreds of star systems within a 50 light-year radius, each potentially harbouring the planetary disk from which this wandering ice ball might have originated. The comet's velocity vector carries additional information encoded in its three-dimensional trajectory through space. As it sweeps past our Sun, Borisov follows a path that will eventually carry it toward the constellation Telescopium, never to return. The hyperbolic excess velocity, that crucial mathematical fingerprint of interstellar origin, measures approximately 32 kilometers per second. This number represents the minimum speed the comet possessed when it first entered our solar system's gravitational influence, still carrying momentum from whatever stellar encounter originally ejected it into the galactic wilderness. Precise astrometric measurements reveal subtle perturbations in the comet's orbit as it approaches perihelion. These deviations from pure gravitational motion arise from non-gravitational forces, the rocket-like effect of sublimating gases escaping from the nuclear surface. Unlike native solar system comets, whose outgassing patterns have been studied for decades, Borisov exhibits peculiar asymmetries in its gas production that hint at an unusual internal structural composition. Radio astronomers detect carbon monoxide emissions from the comet's expanding coma, allowing them to measure gas velocities with extraordinary precision. The molecular emission lines appear Doppler-shifted by amounts that correspond to expansion velocities of several hundred meters per second. These measurements provide direct evidence of active sublimation processes occurring across the nuclear surface, transforming ancient interstellar ices into the ethereal tails that make the comet visible from Earth. Photometric observations track the comet's brightness variations over time, revealing a rotation period of approximately 25 hours. This leisurely tumble suggests either a spherical nucleus or a rotational axis nearly aligned with Earth's line of sight. The light curve shows minimal variation, perhaps 10%, indicating a relatively uniform surface composition, without the dramatic bright and dark regions typical of many solar system comets. Only took millions of years of cosmic ray bombardment to create such uniform, weathering across an object barely larger than a terrestrial mountain. Spectroscopic analysis reveals the presence of multiple molecular species in the comet's coma. Water vapor dominates the emission spectrum, as expected for any icy object approaching the Sun. but the secondary species tell a more complex story. Carbon monoxide appears in unusually high concentrations relative to water, suggesting formation temperatures significantly lower than those typical of our solar system's comet-forming regions. Cyanogen and diatomic carbon contribute additional spectral lines that speak to chemical processes occurring in the comet's tenuous atmosphere. The challenge of measuring accurate chemical abundances from ground-based observations pushes spectroscopic techniques to their limits. Earth's atmospheric water vapor interferes with observations of the comet's water emission lines, while turbulence and seeing conditions blur the delicate structure of molecular spectra. Space-based observations from the Hubble Space Telescope provide cleaner data, but even these measurements carry uncertainties that propagate through theoretical models of comet composition and structure. Dynamical simulations attempt to model the comet's long-term orbital evolution under the combined influence of solar gravity and non-gravitational forces. The calculations reveal complex feedback loops between mass loss, surface erosion, and orbital mechanics that gradually alter the comet's trajectory over multiple perihelion passages. But Borisov will experience only one such passage through our solar system before escaping forever into interstellar space, carrying away whatever secrets its nucleus might contain. As the comet reaches closest approach to the Sun in early December 2019, telescopic observations intensify. This represents humanity's first detailed study of an active interstellar comet, providing unprecedented insights into the physical and chemical processes that shaped planetary formation around other stars. Yet for every question, answered by careful measurement and analysis, several new mysteries emerge from the data. Statistical analysis of Borisov's discovery raises uncomfortable questions about observation bias and detection efficiency. If one interstellar comet becomes visible every few years, how many smaller objects pass through undetected? How many inactive rocky bodies traverse our solar system without developing the conspicuous comae that make optical detection possible? The mathematics suggest a vast population of interstellar wanderers moving through local space, most of them invisible to current survey techniques. Contemporary sky surveys detect approximately one interstellar object every 2 to 3 years, but this rate reflects severe observational limitations rather than the true abundance of such visitors. Objects smaller than a few hundred meters across remain undetectable unless they approach very close to Earth or the Sun. Theoretical models predict that interstellar objects outnumber native asteroids and comets in certain size ranges, transforming our understanding of the solar system's population dynamics. The realization dawns slowly across the astronomical community. We inhabit a region of space that serves as a crossroads for debris from countless other stellar systems. Every cubic kilometer of interplanetary space contains, on average, several interstellar particles moving at velocities too high to have originated locally. Most are too small to detect individually, but their collective presence gradually alters the chemical composition of zodiacal dust and potentially influences planetary atmospheres over geological timescales. Only took 40 years of serious asteroid surveys to discover that our solar system functions as a gravitational lens, focusing interstellar material toward Earth's orbital neighborhood where human civilization happens to reside. The ancient journey begins in darkness, somewhere among the scattered stars of the Milky Way's outer spiral arm, 4.5 million years ago, when early hominids first walked upright across African savannas. A dirty snowball no larger than a city block tumbled through the gravitational chaos surrounding a young stellar system. Perhaps a massive planet swept too close during its orbital migration. Or maybe a stellar companion passed through the system's outer reaches, disturbing the delicate architecture of its comet cloud. Whatever the mechanism, this particular fragment of primordial ice found itself ejected from its birth system with enough velocity to escape the parent star's gravitational embrace forever. The comet that would eventually receive the designation 2I Borisov carries within its frozen nucleus the chemical signature of alien world-building processes. Its ices condensed from a protoplanetary disk enriched with heavy elements forged in the nuclear furnaces of previous stellar generations. Carbon monoxide, methane, ammonia, and complex organic molecules lock themselves into crystalline matrices as temperatures dropped below the condensation thresholds that govern ice formation in the outer regions of planetary systems. Each layer of accumulated frost preserves a record of changing conditions during the comet's formation epoch, like tree rings encoding seasons of drought and abundance. For millions of years, this wandering fragment drifts through the near vacuum of interstellar space, following a trajectory that curves slowly under the gravitational influence of nearby stars. Cosmic rays bombard its surface continuously, gradually darkening its ices and creating a thin crust of organic polymers that will later give the comet its characteristic reddish coloration. Occasionally, microscopic dust grains slam into the nucleus at velocities of dozens of kilometers per second, excavating tiny craters and mixing surface materials with the deeper interior layers. The interstellar medium through which Borisov travels proves far from empty. Hydrogen atoms, at an average density of 1 per cubic centimeter, accumulate on the comet's surface like the slowest snowfall imaginable. Helium, oxygen, and trace amounts of heavier elements contribute additional material to the growing mantle of interstellar contamination. These atoms, formed during the universe's first few minutes, or forged in stellar cores billions of years ago, embed themselves in the comet's crystal lattice, becoming part of its geological record. Temperature regulation in the depths of space depends entirely on the balance between absorbed cosmic radiation and thermal emission. The comet's surface stabilizes at roughly 3 degrees above absolute zero, cold enough to preserve even the most volatile molecular species for geological ages. Water ice remains as rigid as granite under these conditions, while carbon monoxide and nitrogen exist as crystalline solids harder than terrestrial rock. The nucleus becomes a time capsule, preserving chemical information about stellar nucleosynthesis processes that occurred long before our solar system formed. Gravitational perturbations from passing stars occasionally alter the comet's trajectory by small amounts, gradually steering it toward an eventual encounter with our solar system. The cumulative effect of thousands of such interactions over millions of years guides the wandering ice ball through a complex path that intersects with our Sun's gravitational sphere of influence sometime during the early 21st century. Only took 45,000 centuries of patient wandering to arrive at humanity's doorstep, just as our species develops the technological capability to recognize visitors from other worlds. As Borisov crosses the heliopause and enters our solar system's domain, its surface begins to change for the first time in millions of years. Solar radiation, though still faint at distances beyond Neptune's orbit, starts to penetrate the uppermost layers of accumulated interstellar dust. Sublimation proceeds at an imperceptible rate, releasing perhaps a few molecules per square meter per second from the most volatile surface deposits. This earliest phase of cometary activity remains invisible to telescopic observation, producing a coma so tenuous that it contains fewer particles than the best laboratory vacuum. The comet's nucleus rotates with a period of roughly 25 hours, a leisurely tumble that may reflect its formation history or subsequent collisional evolution during the interstellar journey. Each rotation exposes different regions of the surface to solar radiation, creating subtle temperature variations that drive preferential sublimation from areas enriched in volatile species. These processes gradually sculpt the nuclear surface, potentially exposing fresh material from the interior layers that have remained unaltered since the comet's formation epoch. Spectroscopic analysis of the developing coma reveals isotopic ratios that encode information about nucleosynthetic processes in the comet's parent star system. The ratio of carbon-12 to carbon-13, for example, depends on the efficiency of convective mixing in stellar interiors and the star's initial mass and metallicity. Similarly, oxygen isotope ratios reflect the relative contributions of different types of supernova explosions to the chemical enrichment of the comet's formation environment. Radio observations detect the characteristic emission lines of carbon monoxide as molecules escape from the warming nucleus. The line profiles exhibit subtle asymmetries that provide clues about gas velocities and temperature distributions within the expanding coma. These measurements represent humanity's first direct sampling of material formed around another star, offering insights into planetary formation processes that occurred under entirely different physical conditions than those that shaped our own solar system. As the comet approaches perihelion, sublimation rates increase exponentially with decreasing heliocentric distance. The nucleus loses approximately 20 kilograms of material per second at its closest approach to the Sun, a mass loss rate that sounds dramatic but represents only a tiny fraction of the comet's total mass. Most of this material consists of water vapor and entrained dust particles, but minor species like carbon monoxide, methane, and complex organics contribute distinctive spectral signatures that allow detailed compositional analysis. The remarkable preservation of volatile materials during Borisov's interstellar journey demonstrates the extreme cold and radiation environment of interstellar space. Molecules that would decompose rapidly under terrestrial conditions remain stable for millions of years when frozen in cometary ices and shielded from intense stellar radiation. This preservation mechanism allows interstellar comets to function as chemical messengers, carrying information about stellar and planetary formation processes across vast distances and timescales. Yet mystery shrouds the comet's ultimate origin story. Stellar kinematics calculations suggest several possible parent systems within 50 light-years of our current galactic position, but none can be identified with certainty as Borisov's birthplace. The comet's trajectory may have been altered by multiple stellar encounters during its interstellar journey. Erasing the direct connection to its formation environment only took a few million years of galactic orbital motion to scramble the dynamical evidence that might otherwise point toward the specific star system where this ancient wanderer first condensed from interstellar gas and dust. The revolution unfolds quietly in climate-controlled rooms filled with humming computers and the soft clicking of robotic telescope mounts. Across the globe, automated sky surveys methodically photograph the same patches of starfield night after night, their sensitive electronic detectors capturing photons that have travelled for years or centuries to reach Earth. The Catalina Sky Survey in Arizona, Linear in New Mexico, NEOWISE in its solar orbit, and dozens of smaller programs collectively scan approximately 10,000 square degrees of sky each clear night, building an ever-expanding catalogue of moving objects in the solar system. Until recently, these surveys operated under the comfortable assumption that virtually everything they detected originated within our Sun's gravitational domain. Asteroids traced elliptical paths through the inner solar system, while comets followed more eccentric orbits that carried them far beyond Neptune before returning for periodic encounters with solar radiation. The occasional hyperbolic trajectory could be explained by gravitational scattering from Jupiter or Saturn, accelerating native objects beyond escape velocity and ejecting them into interstellar space. This framework began to crumble on October 19th, 2017, when the Pan-STARRS Survey Telescope in Hawaii detected an object moving across the constellation Cancer with a velocity that defied conventional explanation. The preliminary orbit calculation suggested an eccentricity greater than unity, a mathematical impossibility for any object bound to our solar system. Follow-up observations confirm the unprecedented nature of this discovery. 1. Oumuamua, the first confirmed interstellar visitor to pass through our cosmic neighbourhood. The detection of Oumuamua triggered a fundamental reassessment of survey capabilities and observational biases. If one interstellar object could evade detection until it had already passed closest approach to the Sun and begun its exit trajectory, how many others had transited the inner solar system unnoticed? Statistical analysis of the discovery circumstances suggested that similar objects passed through our region of space several times per year, most of them too faint or fast-moving to register on existing surveys. Contemporary improvements in detector technology and data processing algorithms have dramatically enhanced the sensitivity of sky surveys to unusual objects. Machine learning systems now scan through millions of nightly observations, identifying subtle motion patterns that human observers might overlook. These automated classification algorithms excel at detecting the characteristic signatures of hyperbolic trajectories, the telltale mathematical fingerprints of interstellar origin. The discovery rate of potentially interstellar objects has increased exponentially since 2017, though most candidates require weeks of follow-up observation to confirm their exotic origins. Ground-based telescopes around the world coordinate their efforts to track promising targets. Measuring precise positions that allow orbital determination with sufficient accuracy to distinguish between native and foreign objects only takes a few nights of careful astrometry to determine whether a newly discovered visitor will return in a few decades or continue outward into the galactic depths, never to be seen again. NEO-WISE, originally designed to survey asteroids and comets at infrared wavelengths, proves particularly effective at detecting interstellar objects because their unusual thermal properties often distinguish them from solar system natives. Objects that have spent millions of years in the deep cold of interstellar space exhibit surface temperatures and thermal inertia values that differ subtly from asteroids heated by billions of years of solar radiation cycles. The large survey of space and time, scheduled to begin operations from Chile in the coming years, promises to revolutionize interstellar object detection through its unprecedented combination of sensitivity, field of view, and temporal coverage. This facility will photograph the entire visible sky twice each week, potentially detecting hundreds of interstellar visitors per year and providing the statistical foundation necessary to understand the true abundance and characteristics of these cosmic wanderers. Radar observations contribute additional capabilities for characterizing nearby interstellar objects, though the technique works only for targets that pass within a few million kilometers of Earth. The Arecibo Observatory successfully obtained radar echoes from Oumuamua, despite its small size and rapid motion, measuring its rotation period and constraining its shape and surface roughness. These active sensing techniques provide information about object properties that remain invisible to passive optical and infrared observations. Space-based telescopes offer complementary advantages for interstellar object studies, particularly freedom from atmospheric disturbances and access to ultraviolet and X-ray wavelengths blocked by Earth's atmosphere. The Hubble Space Telescope has observed every confirmed interstellar visitor discovered since 2017, providing high-resolution images and spectra that reveal details about surface composition and internal structure. Amateur astronomers contribute significantly to interstellar object follow-up campaigns, using modest equipment to obtain astrometric measurements that help refine orbital calculations. These observations prove particularly valuable for faint objects that challenge the capabilities of large professional telescopes, demonstrating that important scientific discoveries sometimes emerge from unexpected collaborations between professional and citizen scientists. The growing catalogue of interstellar detections reveals troubling patterns in our observational coverage. Most confirmed visitors were discovered only after passing perihelion, when solar heating made them bright enough for detection by existing surveys. This observational bias means that the majority of interstellar objects remain invisible until they venture deep into the inner solar system, where their hyperbolic trajectories become obvious, but opportunities for detailed study prove limited. Theoretical models based on stellar dynamics and planetary formation processes predict that thousands of interstellar objects larger than 10 meters in diameter traverse our solar system each year. Current surveys detect perhaps 1% of these visitors, creating a vast blind spot in our understanding of the local interstellar environment. The objects we do observe represent only the brightest members of a much larger population that includes rocky asteroids, icy comets, and potentially stranger categories of debris ejected from other stellar systems. Statistical analysis of discovery dates and orbital parameters suggests seasonal variations in interstellar object detection rates, possibly reflecting the geometry of Earth's orbit around the Sun and the resulting changes in sky coverage by ground-based surveys. These temporal patterns complicate efforts to derive unbiased estimates of the true arrival rate and size distribution of interstellar visitors. The realization dawns gradually across the astronomical community that our solar system functions as a crossroads for material ejected from planetary formation processes throughout the local galaxy. Every few hours, on average, an object larger than a basketball passes through the space between Earth and the Moon, carrying with it chemical information about stellar nucleosynthesis and planet-building processes that occurred light-years away and millions of years ago. Only took a few decades of serious sky surveys to discover that we inhabit a cosmic shooting gallery, with most of the projectiles remaining invisible until they venture close enough to Earth that collision becomes a genuine possibility. The first confirmed interstellar visitor arrives like a ghost made of starlight and mathematics. On October 19th, 2017, the Pan-STARRS telescope in Hawaii captures a faint streak of light moving across the constellation Cancer at an impossible velocity. Initial orbital calculations suggest something unprecedented, an object following a hyperbolic trajectory with an eccentricity of 1, 2 carrying excess velocity that can only be explained by an origin beyond our solar system's gravitational boundary. The discoverers name it One-Eye Oumuamua, using the Hawaiian word for scout, or messenger from a far arriving first. The designation proves prophetic in ways the astronomers cannot yet imagine. This wandering fragment of another world's formation process exhibits behaviours that challenge fundamental assumptions about cometary physics and planetary debris. Its elongated shape, tumbling rotation, and unusual acceleration patterns create puzzles that persist long after the object disappears into the darkness beyond Neptune's orbit. Oumuamua measures roughly 400 meters in length and perhaps 40 meters in width, resembling a cosmic cigar or needle spinning end over end as it travels through space. No known asteroid or comet exhibits such extreme proportions, suggesting formation processes entirely different from those that shaped objects in our solar system. The elongated geometry might result from tidal forces during a close stellar encounter, collisional fragmentation, or accretion processes occurring under different gravitational conditions than those present during our Sun's planetary formation epoch. Photometric observations reveal a rotation period of 7, 3 hours and brightness variations exceeding a factor of 10 as different aspects of the object's surface rotate into view. This dramatic light curve indicates either extreme elongation or a highly irregular shape with prominent ridges and valleys that reflect sunlight preferentially from certain orientations. The tumbling motion appears chaotic, possibly resulting from collisional impacts or outgassing torques that have accumulated over millions of years of interstellar travel. Spectroscopic analysis proves frustratingly difficult due to the object's rapid motion and increasing distance from Earth. The few successful observations reveal a surface composition similar to organic-rich asteroids found in the outer regions of our solar system, with a reddish colour that suggests long-term exposure to cosmic radiation. Yet subtle differences in the spectral features hint at chemical processes that occurred under different stellar environments, possibly around a star with different metallicity or radiation output than our Sun. The mystery deepens when precise astrometric measurements detect a small but significant deviation from the purely gravitational trajectory predicted by celestial mechanics. Oumuamua accelerates away from the Sun at a rate of approximately 5 AGs 10 to 6 meters per second squared, a tiny force that nevertheless exceeds the uncertainties in orbital determination. This non-gravitational acceleration typically indicates outgassing from a comet nucleus, but Oumuamua shows no visible signs of cometary activity, no coma, no tail, no detectable gas or dust emission. Radio telescopes scan the object for artificial signals, though the search yields only cosmic silence. The Breakthrough Listen project dedicates precious observing time to monitoring Oumuamua across multiple frequency bands, seeking any evidence of technology or communication from the mysterious visitor. The negative results provide important scientific constraints while simultaneously fueling speculation about the object's ultimate nature and origin. Radar observations from the Arecibo Observatory provide the most detailed information about Oumuamua's physical properties, measuring its spin state and constraining its three-dimensional shape through analysis of echo delays and Doppler broadening. These active sensing measurements confirm the extreme aspect ratio suggested by optical photometry, while revealing additional details about surface roughness and internal density distribution. The object's trajectory carries it past Earth at a distance of approximately 24 million kilometers, close enough for detailed study but far enough to preclude any direct sampling missions with existing spacecraft technology. NASA briefly considers whether any existing deep space probe might be redirected for a flyby encounter. But the geometry proves prohibitive for rendezvous with an object travelling at such extreme velocity relative to conventional planetary orbits. Theoretical models struggle to explain Oumuamua's unusual acceleration without invoking exotic physics or artificial origins. Conventional outgassing models require the presence of volatile materials that should produce detectable emission signatures. Yet no such emissions are observed despite intensive monitoring by space-based and ground-based telescopes. Alternative explanations include radiation pressure acting on an unusually low-density object, magnetic interactions with the solar wind, or more speculative mechanisms involving dark matter or modified gravitational theories. The acceleration vector points roughly away from the Sun, consistent with radiation pressure or outgassing effects, but the magnitude exceeds theoretical predictions by factors of several to 10 depending on assumptions about surface composition and internal structure. This discrepancy suggests either unknown physical processes or measurement errors that somehow eluded multiple independent observational campaigns. As Oumuamua recedes beyond the detection limits of terrestrial telescopes, astronomers realize they have witnessed something unprecedented in the history of solar system exploration. This first confirmed messenger from another star system has raised more questions than it answered, challenging conventional models of planetary formation, cometary physics, and interstellar space environment. Only took a few months of intensive observation to discover that our understanding of cosmic debris and planetary system architecture contains fundamental gaps that may require decades of additional research to resolve. The object's departure trajectory carries it toward the constellation Pegasus, at a velocity that will eventually take it beyond the gravitational influence of our galaxy's stellar population. In a few million years, Oumuamua will drift through the intergalactic medium, carrying with it whatever secrets its formation and composition might reveal about planet-building processes in alien stellar systems. Long-term monitoring campaigns attempt to track Oumuamua's fading signal as it moves beyond Jupiter's orbit, but the object becomes too faint for detection by early 2018. Its brief passage through our solar system provides humanity's first direct encounter with material formed around another star, offering tantalizing glimpses of physical and chemical processes that occurred under entirely different conditions than those present during our own planetary system's formation. Statistical analysis of Oumuamua's discovery circumstances suggests that similar objects pass through our region of space approximately once per year, though most remain undetected due to observational limitations and unfavorable viewing geometry. The realization that interstellar visitors arrive this frequently transforms our understanding of the solar system's place in the broader galactic environment, revealing Earth as a planet that orbits through a constant stream of debris from other worlds. The space between stars, once imagined as perfect vacuum punctuated by occasional hydrogen atoms, reveals itself through careful observation to be a crowded highway of wandering debris. Each cubic parsec of the local interstellar medium contains approximately one object larger than a kilometer in diameter, drifting at velocities of 10 to 50 kilometers per second relative to nearby stellar systems. These fragments represent the accumulated detritus of billions of years of planetary formation, stellar encounters, and gravitational ejection events that have scattered material throughout the galaxy's spiral arms. Theoretical models based on stellar dynamics and planetary formation efficiency predict that every star system ejects between 10 billion and 1 trillion objects during its first 100 million years of existence. Young planets migrate inward and outward under gravitational torques from protoplanetary disks, disrupting the orbits of smaller bodies and flinging them into interstellar space at hyperbolic velocities. Close encounters between binary star components can destabilize entire planetary systems, launching comets and asteroids on trajectories that carry them far beyond their parent star's gravitational influence. The cumulative effect of these ejection processes over galactic history has populated interstellar space with a vast reservoir of planetary debris moving in complex patterns that reflect the gravitational influence of stellar motions, spiral density waves, and galactic rotation. Computer simulations suggest that the local stellar neighborhood contains roughly one interstellar object per cubic astronomical unit, a density comparable to the asteroid belt's population in the inner solar system. This hidden population remains largely invisible to conventional astronomical surveys because most interstellar objects emit no light of their own and reflect insufficient starlight for detection at typical encounter distances. Only when such visitors pass within a few astronomical units of our Sun do they become warm enough to act as volatiles, or bright enough to register on sensitive electronic detectors. The objects we observe represent the tip of an enormous iceberg whose bulk remains concealed in the darkness between planetary systems. Gravitational focusing effects enhance the apparent density of interstellar objects in the inner regions of stellar systems, as hyperbolic trajectories bend toward the central star under gravitational attraction. This focusing mechanism increases the number density of interstellar visitors near Earth's orbit by approximately a factor of 2 compared to the general interstellar background, creating a slight enhancement in collision probabilities that accumulates over geological timescales. Chemical analysis of the few confirmed interstellar visitors reveals isotopic signatures that encode information about stellar nucleosynthesis processes occurring throughout the local galaxy. The ratio of oxygen-16 to oxygen-18, for example, depends on the efficiency of helium burning in massive stars and the relative contributions of different supernova types to galactic chemical evolution. Each interstellar object carries within its atomic structure a record of the stellar environments where its constituent elements were forged. Spectroscopic observations detect organic molecules in the outgassing comet of active interstellar comets, suggesting that complex chemistry occurs routinely during planetary formation processes around other stars. These carbon-based compounds, including amino acid precursors and nucleotide bases, provide direct evidence that the molecular building blocks of life form spontaneously in diverse stellar environments throughout the galaxy. The size distribution of interstellar objects follows a power law similar to that observed for asteroids and comets within our own solar system, but with subtle differences that reflect varying ejection efficiencies for different size ranges. Objects smaller than 10 meters in diameter appear overrepresented in the interstellar population, possibly because gravitational scattering preferentially ejects low-mass debris while retaining larger bodies in bound orbits around their parent stars. Dynamical analysis reveals that interstellar objects approach our solar system from all directions with roughly equal probability, indicating that the local interstellar medium exhibits no strong directional bias in its debris population. This isotropy suggests efficient mixing processes have homogenized the distribution of ejected material over timescales much longer than individual stellar orbital periods around the galactic center. Collision cross-sections between interstellar objects and planets depend on encounter velocities that typically exceed orbital speeds by factors of 2 to 5, resulting in impact energies significantly higher than those produced by native solar system debris. These high-velocity collisions create distinctive crater morphologies and shock metamorphism signatures that might be preserved in planetary geological records, providing potential evidence for ancient interstellar bombardment events. The discovery rate of confirmed interstellar visitors has increased dramatically since 2017, from 0 detections per year to approximately 1 confirmed object every 18 months. This acceleration reflects improvements in survey sensitivity and data processing algorithms rather than changes in the underlying arrival rate, suggesting that dozens of interstellar objects have passed through our solar system undetected during the past century of astronomical observation. Machine learning algorithms now scan through millions of nightly observations from automated sky surveys, identifying motion patterns characteristic of hyperbolic trajectories, and flagging candidates for follow-up observation. These artificial intelligence systems excel at recognizing subtle deviations from the orbital patterns typical of native asteroids and comets, potentially increasing the detection efficiency for interstellar visitors by orders of magnitude. Radio astronomy provides complementary detection capabilities for interstellar objects that approach close to Earth, using radar echoes to measure precise distances, rotation rates, and surface roughness properties invisible to optical telescopes. These active sensing techniques work only for targets within a few million kilometers of Earth, but they provide detailed physical characterization impossible through passive observation alone. The growing catalogue of interstellar detections reveals troubling gaps in our observational coverage, particularly for objects approaching from directions near the Sun where solar glare overwhelms ground-based telescopes. Space-based surveys operating at infrared wavelengths offer partial solutions to this visibility problem, but even the most sensitive instruments remain blind to small objects until they venture close enough to warm significantly under solar radiation. Statistical extrapolation from confirmed detections suggests that objects larger than 1 meter in diameter pass within Earth's orbital distance from the Sun approximately once per week, while smaller debris transits this region continuously at rates of thousands of objects per day. Most of this material remains undetectable with current technology, creating an invisible population of interstellar visitors whose properties and origins can only be inferred from theoretical models and limited observational samples. Only took 40 years of dedicated asteroid surveys to realize that our solar system serves as a gravitational lens, concentrating interstellar debris in the inner planetary region where human civilization happens to have evolved. The implications ripple through fields ranging from planetary defense to astrobiology, as scientists grapple with the recognition that Earth orbits through a constant stream of material ejected from other worlds. The mathematics of orbital mechanics describe how gravitational forces sculpt the trajectories of objects moving through space, but they also reveal the subtle ways that stellar systems interact with the broader galactic environment. Our Sun, along with its retinue of planets, asteroids, and comets, moves through the Milky Way at approximately 220 kilometers per second relative to the galactic center. This motion carries the entire solar system through regions of varying stellar density, encountering debris fields ejected from other planetary systems over millions of years of galactic evolution. Gravitational interactions between our solar system and the background population of interstellar objects create complex deflection patterns that occasionally redirect wandering debris toward the inner planetary region. The combined gravitational influence of Jupiter and Saturn acts as a focusing mechanism, bending hyperbolic trajectories and increasing the probability that interstellar visitors will pass close to Earth's orbital distance. This gravitational lensing effect enhances the apparent density of foreign objects in the terrestrial planet zone by factors of 2 to 5 compared to the general interstellar background. Computer simulations reveal that approximately one interstellar object larger than 10 meters in diameter passes within 1 astronomical unit of the Sun every few months, though most remain undetectable due to their small size and lack of visible outgassing. The majority follow trajectories that carry them through the outer solar system without approaching close enough to the inner planets for easy observation, creating observational selection effects that bias our understanding of the true interstellar population. Close gravitational encounters with Jupiter can dramatically alter the trajectories of interstellar visitors, sometimes trapping them temporarily in elliptical orbits that resemble those of conventional comets. These captured objects may complete several orbits around the Sun before subsequent planetary encounters either eject them back into interstellar space or send them crashing into planetary surfaces. The Tisserand parameter, a mathematical quantity that characterizes orbital energy and angular momentum, provides a useful diagnostic for distinguishing between native and temporarily captured interstellar objects. The orbital inclinations of confirmed interstellar visitors exhibit a roughly uniform distribution, indicating that they approach our solar system from all directions with equal probability. This isotropy suggests that the local interstellar medium contains no strong directional bias in its debris population, consistent with efficient mixing processes that have homogenized the distribution of ejected material over timescales much longer than individual stellar orbital periods. Perihelion distances for known interstellar objects cluster between 0.3 and 2.0 astronomical units, reflecting observational biases that favor detection of visitors that approach close enough to the Sun for solar heating to trigger visible outgassing or enhance reflected light signatures. Objects that pass through the outer solar system without venturing inside Jupiter's orbit remain largely invisible to current survey programs, creating substantial blind spots in our census of interstellar traffic. The velocity vectors of interstellar visitors carry information about their origins and the dynamical processes that ejected them from their parent stellar systems. Objects moving slowly relative to the local standard of rest likely originated from nearby stars within a few tens of light years, while high-velocity objects may have travelled much greater distances or experienced multiple gravitational encounters during their interstellar journeys. Statistical analysis of orbital elements reveals subtle correlations between approach velocity, perihelion distance, and object size that provide clues about ejection mechanisms and subsequent evolutionary processes. Small objects exhibit a wider range of orbital parameters than larger ones, possibly reflecting different ejection efficiencies or survival rates during long-duration interstellar travel through environments filled with cosmic radiation and microscopic dust grains. Resonant interactions with planetary orbits can temporarily stabilize the trajectories of some interstellar visitors, creating quasi-periodic orbits that persist for thousands of years before chaotic evolution eventually leads to ejection or collision. These temporary capture scenarios explain how apparently native objects might actually represent interstellar debris that has been gravitationally bound to our solar system for extended periods. The discovery of active interstellar comets like 2I Borisov demonstrates that volatile materials can survive millions of years of exposure to cosmic radiation and interstellar dust bombardment. This preservation mechanism allows interstellar visitors to carry chemical information across vast distances, providing direct samples of material formed around other stars and enabling comparative studies of stellar nucleosynthesis and planetary formation processes. Non-gravitational forces arising from outgassing or radiation pressure can significantly perturb the orbits of small interstellar objects, creating accelerations that exceed the precision of conventional gravitational models. These perturbations complicate efforts to backtrack visitor trajectories to their points of origin, often requiring sophisticated numerical integration techniques that account for multiple physical effects acting simultaneously. The orbital geometry of Earth's annual motion around the Sun creates seasonal variations in the apparent approach directions of interstellar objects. With enhanced detection probabilities during certain times of year, when ground-based telescopes have optimal viewing access to regions of sky where hyperbolic trajectories become most obvious. These geometric effects must be carefully considered when deriving unbiased estimates of interstellar object arrival rates and directional distributions. Gravitational perturbations from the other planets gradually modify the trajectories of long-period interstellar visitors, sometimes altering their orbital parameters sufficiently to change their classification from hyperbolic to elliptical or vice versa. These secular evolution processes operate over timescales of centuries to millennia, potentially obscuring the true origins of objects that have spent extended periods within our solar system's gravitational influence. The increasing precision of astrometric measurements enables detection of subtle orbital perturbations that reveal previously unknown physical processes affecting interstellar object motion. Tiny accelerations arising from anisotropic thermal emission, magnetic interactions with the solar wind, or exotic physics beyond the standard model might become detectable as observational accuracy continues to improve through advances in detector technology and data analysis techniques. Only took a few decades of precise orbital determination to discover that the trajectories of interstellar visitors encode a complex history of gravitational interactions, physical erosion, and evolutionary processes that span millions of years and light-years of travel. Each confirmed detection represents a cosmic archaeology project, requiring careful analysis of orbital mechanics, surface composition, and dynamical history to reconstruct the conditions present during the object's formation and subsequent journey through the galaxy's depths. The Oort cloud, that vast spherical shell of icy debris surrounding our solar system, extends outward to distances of nearly 100,000 astronomical units from the Sun. At these remote distances, solar gravity weakens to the point where passing stars can easily perturb comet orbits, and the boundary between bound and unbound objects becomes increasingly ambiguous. Theoretical models suggest that this outermost region of our solar system contains between 1 and 10 trillion individual comets, most of them dormant and invisible until gravitational disturbances send them careening toward the interplanetary region. Yet the Oort cloud's gravitational architecture proves remarkably porous to interstellar intruders. Objects approaching from interstellar space encounter minimal resistance as they pass through this tenuous reservoir of native comets, following hyperbolic trajectories that carry them deep into the solar system's interior. The cloud's low density, perhaps 1 comet per cubic astronomical unit in its densest regions, means that direct collisions between interstellar visitors and native objects remain extremely rare, occurring perhaps once every few million years for any given interstellar trajectory. Gravitational interactions between interstellar objects and Oort cloud comets can occasionally deflect native material into the inner solar system, triggering comet showers that increase the bombardment rate of terrestrial planets for thousands of years. These perturbation events leave subtle signatures in the orbital distribution of long-period comets, creating temporary enhancements in specific regions of orbital parameter space that gradually disperse under the influence of planetary perturbations. The porosity of our solar system's outer boundary works both ways, allowing not only inward penetration by interstellar debris, but also outward leakage of native material into the galactic environment. Close encounters with passing stars periodically strip comets from the Oort cloud's outer regions, contributing to the general population of interstellar wanderers that pervades the local stellar neighborhood. Over the past 4.5 billion years, our solar system has likely ejected more material into interstellar space than it has captured from external sources. Numerical simulations reveal that the gravitational influence of massive planets like Jupiter and Saturn extends far beyond their immediate orbital neighborhoods, creating weak resonant structures that can trap interstellar objects in temporarily stable orbits. These capture mechanisms operate most efficiently for visitors approaching with relatively low hyperbolic excess velocities, suggesting that nearby stellar systems contribute disproportionately to the population of temporarily captured interstellar debris. The discovery of apparently inactive interstellar objects like 1I Oumuamua demonstrates that not all visitors develop visible Comet as they approach the Sun. These dormant wanderers may represent a significant fraction of the total interstellar population, remaining undetectable until they pass close enough to Earth for direct optical observation or radar ranging. Their dark surfaces and lack of volatile outgassing make them particularly difficult to distinguish from native asteroids without precise orbital determination. Long-term dynamical evolution models predict that some interstellar objects become temporarily captured into quasi-periodic orbits that can persist for thousands to millions of years before chaotic interactions with the major planets eventually lead to ejection or collision. During these extended sojourns, captured objects may be mistaken for native solar system bodies, potentially contaminating our understanding of indigenous asteroid and comet populations. The chemical composition of interstellar visitors provides direct evidence about planetary formation processes occurring around other stars, but contamination by interstellar dust and cosmic ray bombardment can alter surface properties during the long journey between stellar systems. Determining which chemical signatures reflect original formation conditions versus subsequent modification requires careful analysis of exposure age indicators and comparison with theoretical models of interstellar weathering processes. Gravitational perturbations from the galactic tide, the differential gravitational field created by the Milky Way's mass distribution, can significantly alter comet orbits in the Oort cloud's outer regions over timescales of tens of millions of years. These tidal effects create preferred directions for comet injection into the inner solar system that vary with our solar system's position in its galactic orbit, potentially modulating bombardment rates and creating correlations between comet shower timing and galactic dynamics. The boundary between our solar system and interstellar space proves surprisingly permeable to objects in certain size ranges, with ejection and capture efficiencies that depend on complex interactions between gravitational dynamics, radiation pressure, and non-gravitational forces. Objects smaller than approximately 1 kilometer experience significant perturbations from radiation pressure and outgassing forces that can either enhance or inhibit gravitational capture, depending on their physical properties and orbital geometry. Recent discoveries of long-period comets with unusual orbital characteristics raise questions about whether some apparently native objects might actually represent ancient interstellar captures that have been gravitationally bound to our solar system for millions of years. Distinguishing between these possibilities requires detailed analysis of orbital evolution models and comparison with the expected properties of both native and foreign populations. The heliopause, marking the boundary where solar wind pressure balances interstellar medium pressure, provides no barrier to the passage of solid objects moving at typical interstellar velocities. Meter-sized debris crosses this boundary continuously, carrying with it chemical and isotopic information about conditions in nearby stellar systems and the intervening interstellar medium. Statistical analysis of known interstellar object orbits suggests that our solar system's motion through the galaxy creates asymmetries in the apparent arrival directions of interstellar visitors, with enhancement factors of approximately 20% for objects approaching from the direction of solar motion. This geometric effect reflects the combination of our solar system's orbital velocity around the galactic center and random motions of nearby stars relative to the local standard of rest. The detection of multiple interstellar objects within a few years of initiating sensitive sky surveys implies that such visitors have been transiting our solar system throughout Earth's geological history, occasionally colliding with planetary surfaces and contributing exotic material to terrestrial and lunar impact records. Identifying these ancient interstellar impact signatures requires sophisticated geochemical analysis techniques capable of recognizing isotopic anomalies that distinguish extraterrestrial from extrasolar origins. Only took a few years of dedicated interstellar object observations to realize that the boundary between our solar system and the broader galaxy operates more like a porous membrane than a solid barrier, allowing continuous exchange of material in both directions while concentrating certain types of visitors through gravitational focusing effects that increase collision probabilities in the inner planetary region where Earth happens to orbit. The spectroscopic fingerprints of interstellar visitors encode chemical information that spans light years and millions of years, carrying within their molecular signatures the record of stellar nucleosynthesis processes that occurred around entirely different suns. When astronomers point their most sensitive instruments toward active interstellar comets like 2I Borisov, they detect emission lines from familiar molecules, water vapor, carbon monoxide, cyanogen, and diatomic carbon. Yet the relative abundances of these species reveal subtle differences that speak to formation conditions unlike anything present during our own solar system's birth. The ratio of carbon monoxide to water in Borisov's coma exceeds that observed in any native solar system comet by factors of 3 to 10, suggesting formation temperatures significantly lower than those typical of our Sun's protoplanetary disk. This enhanced carbon monoxide abundance indicates that the comet's parent star system experienced different thermal gradients during planetary formation, possibly due to variations in stellar mass, metallicity, or disk structure that affected the condensation sequence of volatile compounds. Isotopic analysis pushes spectroscopic techniques to their absolute limits, requiring hundreds of hours of telescope time to accumulate sufficient signal for meaningful measurements. The ratio of deuterium to hydrogen in interstellar water vapor provides clues about the cosmic ray environment and chemical processing that occurred during the comet's formation epoch. Similarly, the abundance of heavy nitrogen isotopes reflects the efficiency of stellar nuclear synthesis in the parent star and the degree of chemical mixing between different reservoirs of interstellar material. High-resolution spectroscopy reveals complex velocity structures within the expanding comae of active interstellar visitors, indicating non-uniform gas production across the nuclear surface. These velocity patterns arise from preferential sublimation of volatile materials from specific geographic regions, possibly reflecting compositional heterogeneities created during the original accretion process or subsequent modification by cosmic ray bombardment during interstellar travel. The detection of organic molecules in interstellar comet Comet proves particularly challenging because these complex carbon-based compounds produce weak emission lines that overlap with terrestrial atmospheric features and instrumental artifacts. Nevertheless, successful observations have identified formaldehyde, methanol, and hydrogen cyanide in the outgassing from 2I Borisov, demonstrating that complex chemistry occurs routinely during planetary formation processes around other stars. Photodissociation processes in the tenuous comae of interstellar visitors create daughter molecules that provide indirect evidence about parent species residing in the nucleus interior. The detection of CN radicals, for example, indicates the presence of hydrogen cyanide or other cyanogen-bearing compounds that decompose under solar ultraviolet radiation. These chemical genealogies allow astronomers to infer the composition of volatile materials that remain frozen within the nucleus and inaccessible to direct observation. Dust analysis presents additional challenges because the solid particles ejected from interstellar comet nuclei scatter sunlight in ways that depend on grain size, composition, and morphology. Polarimetric observations reveal information about dust particle properties that complement spectroscopic measurements of gas phase molecules, providing a more complete picture of the nucleus composition and internal structure. The color evolution of interstellar comets as they approach and recede from the Sun provides clues about the vertical stratification of volatile materials within their nuclei. Objects that redden significantly during their passage through the inner solar system may be exposing subsurface layers enriched in organic compounds or other species that produce characteristic absorption features at visible wavelengths. Radio astronomy contributes unique capabilities for detecting molecular transitions that remain invisible at optical wavelengths, particularly for species like carbon monoxide that produce strong emission lines at millimeter wavelengths. These observations provide direct measurements of gas temperatures, velocities, and production rates that would be impossible to obtain through optical spectroscopy alone. The challenge of distinguishing contamination by interstellar dust from intrinsic nucleus composition requires careful analysis of temporal variations in spectroscopic signatures as comets approach and recede from the Sun. Material accreted during millions of years of interstellar travel might sublime preferentially during the early phases of solar heating, creating transient spectral features that disappear as deeper nucleus layers become exposed. Space-based spectroscopy offers crucial advantages for interstellar object studies, particularly access to ultraviolet wavelengths where many important molecular transitions occur but remain blocked by Earth's atmospheric absorption. The Hubble Space Telescope has obtained ultraviolet spectra of several interstellar visitors, revealing electronic transitions in small molecules that provide complementary information to ground-based observations of vibrational and rotational transitions. Theoretical models of cometary outgassing struggle to explain the observed production rates and spatial distributions of different molecular species in interstellar visitor comae. The gas dynamics of sublimation from irregularly shaped, rapidly rotating nuclei create complex flow patterns that challenge conventional assumptions about spherically symmetric expansion and collisional thermalization processes. The preservation of volatile compounds during millions of years of interstellar travel demonstrates the remarkable stability of molecular ices under deep space conditions. Carbon monoxide, methane, and even more complex organic molecules remain chemically intact despite continuous bombardment by cosmic rays and occasional impacts by interstellar dust grains travelling at velocities of dozens of kilometers per second. Comparative analysis of spectroscopic data from multiple interstellar visitors begins to reveal patterns that constrain models of planetary formation chemistry around different types of stars. Objects originating from metal-poor stellar environments might exhibit enhanced abundances of primordial molecular species, while those formed around more massive stars could show evidence of enhanced heavy element processing and complex organic synthesis. The discovery that interstellar comets contain familiar molecules in unfamiliar proportions suggests that the basic chemistry of planetary formation operates similarly throughout the galaxy, but with quantitative variations that reflect differences in stellar mass, metallicity, and disk dynamics. These chemical variations provide direct observational constraints on theoretical models of planet formation that previously relied on indirect evidence from exoplanet surveys and meteorite analysis. Only took a few years of intensive spectroscopic observations to realize that interstellar visitors function as chemical messengers, carrying direct samples of material formed around other stars and enabling the first comparative studies of planetary formation chemistry across different stellar environments. Each detected emission line represents photons that encode information about nucleosynthesis processes, thermal histories, and chemical evolution pathways that occurred light years away from our own cosmic neighbourhood. The statistical models that govern cosmic collision probabilities operate on timescales that dwarf human comprehension, yet their implications for planetary evolution and biological development become increasingly clear with each new interstellar detection. Every square metre of Earth's surface presents a target area that intercepts approximately one interstellar particle larger than a grain of sand every 10,000 years, a bombardment rate that seems negligible on human timescales, but accumulates significant effects over geological ages. Current estimates suggest that objects larger than 10 metres in diameter cross Earth's orbital path approximately once every century, while kilometre-sized interstellar visitors approach within collision distance perhaps once every 10 million years. These frequencies remain highly uncertain due to observational biases and limited detection statistics, but they provide a framework for assessing the long-term impact hazard posed by debris from other stellar systems. The velocity distributions of interstellar objects create impact scenarios substantially different from those involving native solar system debris. Collision speeds between Earth and interstellar visitors typically range from 15 to 70 kilometers per second, compared to typical asteroid impact velocities of 10 to 20 kilometers per second. These enhanced velocities translate into kinetic energies that exceed those of comparable native impactors by factors of 2 to 20, creating more energetic explosions and deeper excavation of target materials. Crater formation models predict that interstellar impacts produce distinctive morphological signatures that might be preserved in terrestrial and lunar geological records. The extreme impact velocities generate shock pressures sufficient to create exotic mineral phases and isotopic fractionation patterns that could serve as forensic indicators of extraterrestrial versus extrasolar origins. Identifying these ancient impact signatures requires sophisticated geochemical analysis techniques capable of recognizing subtle chemical anomalies. The flux of interstellar dust particles creates a continuous but barely detectable background contamination of planetary atmospheres, contributing perhaps 1 part in 10 billion to the total mass influx from cosmic sources. These microscopic grains carry isotopic signatures that differ subtly from solar system materials, potentially altering atmospheric chemistry over geological timescales and contributing to the isotopic evolution of planetary volatile reservoirs. Gravitational focusing by the Sun's mass enhances collision probabilities for objects approaching from certain directions, while reducing them for others, creating complex geometric patterns in the spatial distribution of impact hazards. The magnitude of this focusing effect depends on approach velocity and trajectory inclination, with the strongest enhancements occurring for objects following nearly parabolic orbits that graze the solar system's outer boundary. Monte Carlo simulations of long-term bombardment histories suggest that Earth has experienced between 1,000 and 10,000 significant interstellar impacts during its 4.5 billion year history. Most of these events involved objects smaller than 100 meters in diameter, creating explosions equivalent to nuclear weapons but leaving no permanent geological traces. Larger impacts remain extremely rare but could produce effects comparable to major extinction events in Earth's biological record. The timing of interstellar impacts exhibits stochastic variations that depend on our solar system's motion, through regions of varying debris density in the local interstellar medium. Encounters with stellar association remnants or the debris trails from ancient supernovae might temporarily enhance bombardment rates by factors of 10 to 100. Creating brief epochs of increased impact activity separated by longer periods of relative quiescence. Chemical analysis of suspected interstellar impact sites requires distinguishing between contamination signatures that originated in other stellar systems versus those created by terrestrial weathering processes or native solar system materials. Platinum group element abundances, osmium isotope ratios, and raw earth element patterns provide potential discriminants, but the preservation of these signatures over geological timescales remains problematic due to terrestrial alteration processes. The discovery of apparently dormant interstellar objects like one off Oumuamua raises uncomfortable questions about our ability to detect potentially hazardous visitors before they approach dangerously close to Earth. Objects that lack visible Comet or significant thermal emission remain essentially invisible until they pass within a few million kilometers of our planet, providing minimal advance warning for any mitigation efforts that might prove necessary. Current planetary defense surveys focus primarily on native near-Earth asteroids following conventional elliptical orbits, with detection algorithms optimized for objects that return periodically and can be tracked over multiple apparitions. Interstellar visitors approach on hyperbolic trajectories that provide only single opportunities for detection and characterization, requiring entirely different observational strategies and response protocols. The psychological impact of recognizing Earth as a target in a cosmic shooting gallery, populated by debris from other worlds, challenges comfortable assumptions about our planet's isolation and security. Each confirmed interstellar detection reinforces the realization that terrestrial civilization developed within a dynamic galactic environment, where bombardment by foreign materials represents a constant background hazard that fluctuates in intensity over astronomical timescales. Risk assessment for interstellar impact scenarios proves particularly challenging because the size distribution, composition, and arrival rate of potential impactors remain poorly constrained by current observational data. Theoretical models provide order of magnitude estimates, but significant uncertainties persist in almost every parameter that affects collision probability calculations and damage assessments. The potential for delivering organic molecules or even primitive life forms through interstellar panspermia adds biological dimensions to impact probability calculations. Objects originating from planetary systems where life developed might carry dormant microorganisms protected within their interior structures, creating scenarios where interstellar collisions could introduce alien biochemistry to terrestrial environments. Advanced warning systems capable of detecting kilometer-sized interstellar objects at distances of several astronomical units would require space-based telescopes with unprecedented sensitivity and sky coverage. Such systems could provide months or years of advance notice for large potentially hazardous visitors, enabling detailed characterization studies and potentially allowing time for deflection missions if impact trajectories threatened populated regions. Only took a few decades of asteroid impact research to realize that the bombardment environment surrounding Earth includes significant contributions from interstellar sources whose properties, timing, and effects remain largely unknown. Statistical analysis of confirmed interstellar detections suggests that our planet orbits through a cosmic minefield, where the arrival of foreign projectiles represents an ongoing natural hazard that has operated throughout Earth's geological history and will continue indefinitely into the future. The dark fleet drifts silently through our solar system, an invisible armada of objects that follow hyperbolic trajectories without betraying their presence through visible outgassing or reflected sunlight bright enough for detection by conventional surveys. These dormant wanderers represent perhaps 90% of all interstellar visitors. Remaining hidden until chance encounters with planetary radar systems or extremely close passages near Earth reveal their alien origins through precise orbital determination. Current detection methods exhibit severe observational biases that favour the discovery of active comets, developing conspicuous Comet as they approach the Sun, while inactive rocky objects or depleted comet nuclei pass through unnoticed unless they venture within a few 100,000 kilometres of Earth. The handful of confirmed interstellar detections therefore represents only the most visible members of a much larger population, whose true size and characteristics remain largely unknown. Theoretical models based on planetary formation efficiency and stellar dynamics predict that inactive objects outnumber active comets in the interstellar population by factors of 10 to 100, suggesting that hundreds of dormant interstellar visitors transit our solar system each year. These dark wanderers carry no visible signatures of their exotic origins, appearing indistinguishable from native asteroids until careful astrometric measurements reveal velocities that exceed the escape threshold for gravitationally bound objects. The challenge of detecting inactive interstellar objects requires observational strategies fundamentally different from those employed for conventional asteroid surveys, rather than searching for objects that return periodically on elliptical orbits. Astronomers must identify single apparition visitors moving at anomalously high velocities relative to the solar system's gravitational field. This detection problem becomes increasingly difficult for small objects whose apparent motions fall below the precision limits of ground-based astrometric measurements. Radar astronomy provides the most sensitive technique for characterizing nearby interstellar objects, using active illumination to measure precise distances, rotation rates, and surface roughness properties invisible to passive optical observations. The Arecibo Observatory successfully obtained radar echoes from 1I Oumuamua despite its small size and rapid motion, demonstrating that interstellar visitors can be studied in detail when they approach within a few million kilometers of Earth. Space-based telescopes operating at infrared wavelengths offer partial solutions to the visibility problem, detecting thermal emission from objects warmed by solar radiation, even when they reflect insufficient visible light for ground-based detection. The NEWISE mission has identified several asteroids with unusually high orbital velocities that might represent inactive interstellar visitors, though confirmation requires extended observation campaigns to determine precise trajectory parameters. The size distribution of the invisible interstellar population remains highly uncertain because current surveys preferentially detect larger objects while remaining blind to smaller debris that might dominate the total number density. Extrapolation from the few confirmed detections suggests that meter-sized interstellar objects pass within Earth's orbital distance approximately once per week, while smaller fragments transit this region continuously at rates of thousands per day. Chemical analysis of inactive interstellar objects proves particularly challenging, because their surfaces may have been altered by millions of years of cosmic ray bombardment and micrometeorite impacts during interstellar travel. The lack of active outgassing eliminates opportunities for spectroscopic analysis of pristine interior materials, leaving only broadband photometry and polarimetry as tools for constraining surface composition and mineralogy. Long-term monitoring campaigns attempt to track the apparent motion of suspected interstellar objects across multiple observing seasons, but most visitors move too rapidly for extended follow-up observation. Objects discovered near closest approach to the Sun typically fade below detection limits within weeks or months, providing only brief windows for detailed characterization before they disappear into the outer solar system's darkness. The discovery of apparently artificial characteristics in some interstellar visitors, such as Oumuamua's extreme elongation and anomalous acceleration, raises unsettling questions about the nature of debris ejected from other stellar systems. While natural formation processes can likely explain these unusual properties, The possibility of encountering technological artifacts from alien civilizations adds speculative dimensions to interstellar object research that extend far beyond conventional planetary science. Statistical analysis of confirmed interstellar detections reveals troubling gaps in our observational coverage, particularly for objects approaching from directions near the Sun where solar glare overwhelms ground-based telescopes. These blind spots in sky coverage could allow large, potentially hazardous visitors to approach Earth undetected, providing minimal advance warning for any mitigation efforts that might prove necessary. Machine learning algorithms now scan through millions of nightly observations from automated sky surveys, seeking motion patterns characteristic of hyperbolic trajectories that might indicate interstellar origins. These artificial intelligence systems excel at identifying subtle deviations from the orbital patterns typical of native asteroids and comets, potentially increasing detection efficiency by orders of magnitude as computational capabilities continue to improve. The psychological impact of recognizing that our solar system harbors a substantial population of invisible foreign objects challenges comfortable assumptions about cosmic isolation and planetary security. Each confirmed interstellar detection reinforces the realization that Earth orbits through a region of space filled with debris from other worlds, most of it remaining undetected until chance encounters reveal its alien nature. Future survey systems designed specifically for interstellar object detection will require unprecedented combinations of sensitivity, field of view, and temporal coverage to achieve comprehensive census of the dark fleet currently transiting our solar system. The Vera Rubin Observatory, scheduled to begin operations in the coming years, promises to revolutionize interstellar object astronomy through its ability to survey the entire visible sky twice each week with extraordinary sensitivity. The growing recognition that most interstellar visitors remain invisible to current detection methods has profound implications for planetary defense strategies, astrobiology research, and our understanding of the galactic environment surrounding our solar system. Only took a few years of dedicated interstellar object observations to realize that the majority of cosmic traffic through our local space operates below the detection threshold of existing surveys, creating an invisible population whose properties and potential hazards remain largely unknown. The Sun carries our entire planetary system through the galaxy at approximately 220 kilometers per second, tracing a complex orbit that weaves above and below the galactic disk's mid-plane over periods of roughly 60 million years. This orbital motion brings our solar system into contact with debris fields ejected from countless other stellar systems during the past 4.5 billion years of galactic evolution, creating an ever-changing bombardment environment that reflects our current position within the Milky Way's spiral structure. Stellar kinematics reveal that our local neighborhood contains several moving groups of stars that share common velocities and likely originated from the same stellar nurseries millions of years ago. The Hyades cluster, Ursa Major group, and Pleiades association all contribute members whose planetary formation processes have scattered debris throughout our region of the galaxy. As our solar system's orbit carries it through these association remnants, encounter rates with interstellar objects temporarily increase by factors of 2 to 10 above the background level. The galactic tide, created by differential gravitational forces from the Milky Way's mass distribution, perturbs comet orbits in our solar system's outer regions, while simultaneously influencing the trajectories of interstellar objects passing through local space. These tidal effects operate most strongly near the galactic plane, where stellar densities reach their maximum values and gravitational perturbations become correspondingly more frequent and intense. Computer simulations of galactic dynamics predict that our solar system periodically encounters spiral density waves that compress interstellar material and trigger enhanced star formation in nearby regions. These spiral arm passages, occurring roughly every 100 million years, temporarily increase the local density of stellar debris by factors of 5 to 50, creating epochs of enhanced bombardment that might correlate with major extinction events in Earth's biological record. The local bubble, a region of hot tenuous gas surrounding our solar system and extending approximately 300 light-years in all directions, was carved out by supernova explosions over the past 10 to 20 million years. These stellar deaths not only cleared away much of the local interstellar medium, but also accelerated substantial quantities of heavy element debris to velocities sufficient for escape from their parent stellar systems. Theoretical models suggest that supernova shock waves can simultaneously destroy existing interstellar objects through collisional fragmentation, while creating new ones through the disruption of planetary systems caught within their expanding blast zones. The cumulative effect of multiple supernovae within the local bubble has likely enriched our local environment with exotic debris, whose compositions reflect the extreme physical conditions present during stellar collapse and explosion. The discovery that our solar system currently resides within a low-density cavity in the interstellar medium implies that bombardment rates were significantly higher in the past, when we occupied regions of greater stellar density. Geological evidence for impact events on Earth and other planets might therefore exhibit temporal variations that correlate with our solar system's motion through different galactic environments over hundreds of millions of years. Nearby stellar associations continue to eject planetary debris as their member stars complete their planetary formation processes or experience close encounters that destabilize previously stable orbital architectures. The TW Hydrae Association, located roughly 50 light-years away and containing stars only 10 million years old, likely contributes a disproportionate fraction of the interstellar objects currently entering our solar system. The relative motion between our solar system and neighbouring stars creates encounter geometries that focus interstellar debris towards specific regions of our local space. Objects ejected from stars moving in roughly the same direction as our solar system approach with lower relative velocities and higher capture probabilities, while those originating from stars with divergent motion patterns arrive at extreme velocities that preclude gravitational trapping. Gaia spacecraft observations of stellar motions throughout our local galactic neighbourhood reveal complex velocity patterns that reflect ancient stellar encounters, galactic rotation, and perturbations from dark matter substructures. These kinematic data enable reconstruction of stellar trajectories over millions of years, potentially identifying the specific sources responsible for individual interstellar visitors detected by solar system surveys. The chemical composition of nearby stars provides clues about the types of material their planetary formation processes might have ejected into interstellar space. Metal-poor stars formed during earlier epochs of galactic evolution would produce debris with isotopic signatures reflecting different nucleosynthetic pathways, while more recently formed stars incorporate heavy elements created by multiple generations of stellar evolution. Close encounters between our solar system and other stellar systems occur approximately once every million years within distances of 1,000 astronomical units, close enough to significantly perturb the orbits of objects in our Oort cloud, while simultaneously allowing exchange of cometary material between the two systems. These stellar flybys create temporary spikes in both ejection and capture rates that can persist for thousands of years after the encounter. The asymmetric distribution of nearby stars creates directional biases in the arrival patterns of interstellar objects, with enhanced flux from regions containing young stellar associations and reduced flux from directions toward the local bubble's interior. These geometric effects must be carefully considered when interpreting observational data and deriving unbiased estimates of interstellar object properties and abundances. Future astrometric missions will provide increasingly precise measurements of stellar positions and velocities, enabling detailed reconstruction of the dynamical history of our local galactic environment over timescales of tens of millions of years. These data will reveal which specific stellar encounters were responsible for major perturbations of our solar system's architecture and identify the most likely sources for confirmed interstellar visitors. The realization that our solar system's bombardment environment varies systematically with galactic position and stellar neighborhood dynamics has profound implications for understanding the long-term evolution of planetary surfaces, atmospheres, and biological systems. Only took a few decades of galactic astronomy to discover that Earth's impact history reflects not only the chaotic dynamics of our own planetary system, but also the complex gravitational choreography of stellar motions throughout our local region of the Milky Way galaxy. The mathematics of cosmic collision mechanics calculate probabilities that stretch across geological timescales. They're cold equations describing scenarios where interstellar visitors, carrying the isotopic signatures of distant stars, eventually intersect with planetary surfaces in our solar system. Statistical models based on current detection rates and theoretical population estimates suggest that Earth experiences a significant impact from an interstellar object larger than 100 meters in diameter, approximately once every 10 to 100 million years. Frequencies that place such events within the realm of recorded geological history. The velocity distributions of potential interstellar impactors create collision scenarios fundamentally different from those involving native solar system debris. Impact speeds between Earth and foreign objects typically range from 20 to 70 km per second, compared to native asteroid collision velocities of 10 to 20 km per second. These enhanced velocities translate into kinetic energies that exceed those of comparable domestic impactors by factors of 4 to 50, creating explosions equivalent to hundreds of nuclear weapons for relatively modest object sizes. Crater formation models predict that interstellar impacts produce distinctive morphological and chemical signatures that might be preserved in terrestrial and lunar geological records. The extreme impact velocities generate shock pressures sufficient to create exotic mineral phases and isotopic fractionation patterns that could serve as forensic indicators distinguishing extraterrestrial from extrasolar origins. Platinum group element abundances, osmium isotope ratios, and helium-3 concentrations provide potential discriminants, though preserving these signatures over millions of years requires favourable geological conditions. The Chicxulub impact structure, created 66 million years ago by the asteroid collision that contributed to dinosaur extinction, exhibits chemical anomalies that some researchers interpret as evidence for an interstellar origin. The impactor's unusually high concentration of certain platinum group elements and anomalous isotopic signatures of osmium and chromium might reflect formation processes around a different star. Though alternative explanations involving native solar system objects remain viable and perhaps more likely, Tunguska-class airbursts, caused by objects tens of meters in diameter exploding in Earth's atmosphere, occur approximately once per century and would leave minimal geological traces if caused by interstellar visitors. These events could deliver exotic isotopic signatures to terrestrial surface materials without creating obvious crater structures, potentially contributing to the slow accumulation of foreign material in Earth's geological record over millions of years. The lunar surface preserves a more complete impact record than Earth due to the absence of atmospheric protection and geological recycling processes that erase crater evidence over time. Analysis of lunar samples collected during Apollo missions reveals trace concentrations of materials with isotopic signatures that differ subtly from typical solar system compositions, possibly indicating ancient bombardment by interstellar debris during periods of enhanced flux. Ocean impacts by interstellar objects create entirely different scenarios than terrestrial collisions, with most of the exotic material dispersing into seawater and eventually incorporating into marine sedimentary sequences. The isotopic signatures of such events might be preserved in deep-sea cores that sample sediments deposited over millions of years, providing a potential archive of ancient interstellar bombardment that remains largely unexplored. Mass spectrometry techniques capable of detecting isotopic anomalies at parts per million levels now enable identification of potential interstellar contamination in terrestrial samples. Meteorite collections contain occasional specimens with anomalous isotopic signatures that might represent ancient interstellar impacts, though distinguishing these possibilities from contamination by pre-solar grains or measurement artifacts requires extremely careful analytical protocols. The preservation of organic molecules within interstellar impactors raises the possibility that such collisions could deliver complex carbon compounds or even primitive life forms to planetary surfaces through panspermia mechanisms. Objects originating from stellar systems where biological processes developed might carry dormant microorganisms protected within their interior structures, creating scenarios where interstellar impacts could introduce alien biochemistry to terrestrial environments. Computer simulations of large interstellar impacts reveal that objects larger than 1 kilometer in diameter could create global environmental disruptions comparable to major extinction events in Earth's biological record. The enhanced impact velocities typical of interstellar collisions generate more energetic explosions and inject greater quantities of debris into the atmosphere than equivalent impacts by native objects, potentially triggering more severe and long-lasting climatic perturbations. The stochastic nature of interstellar bombardment creates temporal clustering effects where multiple impacts might occur within geologically brief intervals, followed by longer periods of relative quiescence. These clustering patterns reflect the passage of our solar system through regions of varying debris density in the local interstellar medium, potentially correlating with major geological boundaries and biological transitions in Earth's history. Advanced isotopic analysis of impact glasses and shocked minerals from terrestrial crater sites might reveal evidence for ancient interstellar collisions that occurred during Earth's early bombardment period, the Hadean and Archean eons, when impact rates were orders of magnitude higher than present values, likely included substantial contributions from interstellar sources whose signatures could be preserved in the oldest surviving geological formations. The recognition that Earth has experienced thousands of significant interstellar impacts during its 4.5 billion year history challenges conventional assumptions about the isolation of terrestrial chemical and biological evolution. Each such collision represents a potential contamination event that could have introduced exotic materials, altered atmospheric composition, or triggered evolutionary transitions through environmental disruption or the introduction of foreign organic compounds. Future missions to collect samples from confirmed interstellar visitors will provide ground truth for impact scenario modeling, revealing the actual compositions and physical properties of materials that might eventually collide with planetary surfaces. These data will enable more accurate predictions of the environmental consequences and geological signatures expected from future interstellar impact events. Only took a few decades of impact crater research to realize that Earth's bombardment history includes significant contributions from objects formed around other stars, creating collision scenarios with enhanced energies and exotic chemical signatures that have operated as a background hazard throughout our planet's geological evolution. Statistical analysis suggests that such events remain inevitable on timescales relevant to human civilization, though their precise timing and magnitude remain inherently unpredictable. The cosmic perspective emerges slowly from decades of patient observation and careful calculation, revealing Earth as a small world drifting through an ancient shooting gallery, where projectiles arrive from stellar systems scattered across hundreds of light-years of galactic space. Each confirmed interstellar detection reinforces the unsettling realization that our planet orbits within a dynamic environment where bombardment by foreign materials represents not an occasional anomaly, but a fundamental characteristic of existence in the Milky Way galaxy. The sheer scale of interstellar debris populations challenges human comprehension through numbers that stretch across multiple orders of magnitude. Current estimates suggest that our local galactic neighborhood contains approximately 10 billion objects larger than 1 kilometer in diameter, moving at velocities sufficient to traverse interstellar distances, with size distributions that extend downward to include trillions of smaller fragments carrying the chemical signatures of planetary formation processes that occurred throughout the galaxy's evolutionary history. The temporal dynamics of this cosmic bombardment operate on timescales that dwarf geological processes on Earth, yet their cumulative effects have shaped planetary evolution in ways that remain largely unrecognized by conventional theories of solar system development over the past 4.5 billion years. our planet has likely intercepted millions of interstellar particles larger than 1 meter in diameter, each carrying isotopic information about nucleosynthetic processes that occurred in the stellar cores light years away from our Sun. The discovery that active interstellar comets like 3IAtlas carry organic molecules synthesized around other stars provides direct evidence that complex chemistry occurs routinely during planetary formation throughout the galaxy. These carbon-based compounds, including amino acid precursors and nucleotide bases, demonstrate that the molecular building blocks of life form spontaneously in diverse stellar environments, potentially seeding planetary surfaces across vast regions of galactic space. The invisible majority of interstellar visitors remains undetected by current surveys, creating a hidden population whose properties and abundance can only be inferred from theoretical models and limited observational samples. Statistical extrapolation from the few confirmed detections suggests that objects larger than 10 meters in diameter cross Earth's orbital path approximately once per decade, while smaller debris transits this region continuously at rates that exceed the flux of native meteoroids. The chemical contamination of planetary atmospheres by interstellar dust occurs gradually over geological timescales, contributing perhaps 1 part in 10 billion to the total mass influx from cosmic sources. These microscopic contributions carry isotopic signatures that differ subtly from solar system materials, potentially altering atmospheric evolution and contributing to the long-term chemical evolution of planetary volatile reservoirs in ways that remain unrecognized by current atmospheric models. The psychological impact of recognizing Earth's position within this cosmic crossroads challenges anthropocentric assumptions about planetary isolation and terrestrial uniqueness. The materials comprising our planet's surface, atmosphere, and biosphere include trace contributions from stellar nucleosynthesis processes that occurred throughout our local galactic neighborhood, connecting terrestrial geochemistry to the broader cosmic cycles of stellar birth, evolution, and death. The gravitational architecture of our solar system functions as a focusing mechanism that concentrates interstellar debris in the inner planetary region where Earth orbits, enhancing collision probabilities by factors of 2 to 5 compared to the general interstellar background. This gravitational lensing effect means that our planet experiences higher bombardment rates than would occur in truly empty interstellar space, creating enhanced opportunities for chemical and biological contamination by materials formed around other stars. The ongoing revolution in astronomical instrumentation promises to reveal the true scope and characteristics of interstellar traffic through our solar system, with next-generation surveys potentially detecting hundreds of foreign visitors each year. These observations will transform our understanding of the galactic environment surrounding Earth, while providing unprecedented insights into planetary formation processes occurring throughout the Milky Way galaxy. The realization that most stellar systems likely eject substantial fractions of their planetary building materials into interstellar space suggests that our galaxy contains a vast reservoir of homeless debris wandering between the stars. This ejected material represents the failed planets, disrupted asteroids, and scattered comets that never achieved stable orbits around their parent stars, instead beginning million-year journeys that occasionally bring them into contact with other planetary systems. The isotopic diversity observed in confirmed interstellar visitors hints at the tremendous variety of stellar environments that contributed to the galaxy's chemical evolution over billions of years. Objects formed around metal-poor stars, massive short-lived giants, and long-lived red dwarfs each carry distinctive nucleosynthetic signatures that encode information about stellar mass, age, and evolutionary history into the compositions of wandering debris. The statistical inevitability of future interstellar impact creates scenarios where Earth will eventually experience collisions with objects carrying chemical and possibly biological information from other worlds. These events represent potential contamination scenarios that could introduce exotic materials to terrestrial environments or trigger environmental disruptions comparable to major extinction events in Earth's geological record. The search for evidence of ancient interstellar bombardment in terrestrial geological formations has only recently begun, using sophisticated analytical techniques capable of detecting isotopic anomalies that distinguish extraterrestrial from extrasolar origins. Deep drilling projects and meteorite collections provide potential archives of past interstellar impacts that could reveal the long-term history of foreign material delivery to Earth's surface. The growing recognition that our solar system operates as a gravitational crossroads for debris from throughout the local galaxy fundamentally alters our perspective on Earth's place in the cosmic hierarchy. Rather than existing in splendid isolation, our planet orbits through a region of space that serves as a meeting ground for materials ejected from countless other worlds, creating connections between terrestrial evolution and galactic dynamics that span light years and geological ages. Only took a few years of dedicated interstellar object research to discover that Earth exists within a shooting gallery, populated by debris from other worlds, where most projectiles remain invisible until they approach close enough for collision to become a genuine possibility. This realization transforms our understanding of planetary evolution from an isolated local process into a galactic phenomenon that connects the formation and development of worlds across vast regions of interstellar space. The endless vigil begins anew each night as automated telescopes across the globe sweep their electronic eyes across predetermined patches of star-filled darkness, their sensitive detectors capturing photons that have travelled for minutes or millennia to reach Earth. The Catalina Sky Survey in Arizona methodically photographs the same celestial real estate every few nights, comparing images to identify objects that move against the background of distant stars. Linear in New Mexico scans broad swathes of sky with robotic persistence, while smaller facilities in Australia, Chile and Hawaii contribute to a worldwide network of mechanical sentinels that never sleep, never blink, never lose concentration during the long hours before dawn. The expanding catalogue of discovered objects grows by thousands of entries each month, a digital bestiary of asteroids, comets, and space debris that populates the vast emptiness between planetary orbits. Most follow predictable elliptical paths that return them to the inner solar system at regular intervals, their orbital parameters encoded in databases that predict their positions decades into the future. But increasingly, the surveys detect anomalies, objects moving too fast, approaching from impossible directions, following trajectories that speak of origins beyond our sun's gravitational embrace. Each confirmed interstellar detection triggers intensive follow-up campaigns that mobilize telescopes around the world in coordinated efforts to measure precise positions, determine accurate orbits, and characterize physical properties before the visitors fade beyond detection limits. The European Southern Observatory's Very Large Telescope Array in Chile obtains high-resolution spectra that reveal surface compositions and gas production rates. The Hubble Space Telescope dedicates precious observing time to imaging campaigns that constrain object sizes and rotation states. Radio telescopes attempt to detect molecular emissions from outgassing Comet, or obtain radar echoes from nearby visitors. The technological infrastructure supporting this global surveillance network represents one of humanity's most ambitious scientific enterprises, requiring coordination between dozens of institutions across multiple continents and time zones. Data flows continuously from remote mountaintop observatories through fiber optic cables to computing centers where automated algorithms scan millions of nightly observations, seeking the subtle motion patterns that distinguish interstellar visitors from the background population of native solar system objects. Machine learning systems trained on vast databases of known asteroid and comet orbits excel at identifying anomalous trajectories that warrant further investigation. These artificial intelligence algorithms process observational data faster than human astronomers could examine it manually, flagging candidates for interstellar origin within hours of their initial detection. The most promising targets receive priority designation for follow-up observation, triggering alert networks that notify observatories worldwide of objects requiring urgent attention. The Vera Rubin Observatory, scheduled to begin operations from its Chilean mountaintop site in the coming years, promises to revolutionize interstellar object detection through its unprecedented combination of mirror size, camera sensitivity, and field of view. This facility will photograph the entire visible sky twice each week with extraordinary depth, potentially detecting hundreds of interstellar visitors annually and providing the statistical foundation necessary to understand their true abundance and characteristics. Space-based surveys offer complementary capabilities that overcome atmospheric limitations and gain access to infrared wavelengths, where thermally warm objects emit most efficiently. The NEOWISE mission continues to scan the sky at infrared wavelengths, detecting objects through their thermal emission rather than reflected sunlight. Future space telescopes designed specifically for interstellar object surveillance could provide early warning capabilities by detecting visitors while they remain in the outer solar system, months or years before closest approach to Earth. The challenge of distinguishing genuine interstellar visitors from measurement errors, data artifacts, or unusual but native solar system objects requires increasingly sophisticated analysis techniques. Orbital determination algorithms must account for non-gravitational forces arising from outgassing, radiation pressure, and relativistic effects that can mimic the signatures of hyperbolic trajectories. Multiple independent observations from different telescopes provide essential confirmation of preliminary orbital calculations. International cooperation protocols establish procedures for sharing observational data and coordinating follow-up campaigns when potential interstellar objects are discovered. The Minor Planet Center in Cambridge, Massachusetts, serves as a global clearinghouse for astrometric observations, collecting position measurements from observatories worldwide and computing preliminary orbits that identify candidates requiring additional study. Professional astronomers collaborate increasingly with amateur observers whose modest equipment can contribute valuable astrometric measurements for tracking confirmed interstellar visitors. These citizen scientists provide geographic diversity that enables round-the-clock monitoring of rapidly moving targets, demonstrating that important scientific discoveries sometimes emerge from unexpected partnerships between institutional and independent researchers. The psychological evolution of the astronomical community reflects growing acceptance that our solar system receives regular visits from objects formed around other stars. What initially seemed like extraordinary anomalies requiring exotic explanations now appear as natural consequences of galactic dynamics and planetary formation processes operating throughout the Milky Way. The discovery of each new interstellar visitor reinforces patterns that transform isolated detections into elements of a larger cosmic phenomenon. Current surveys detect perhaps 1% of the interstellar objects that actually traverse our solar system, creating observational selection effects that bias our understanding toward the largest, brightest, or most active visitors. The invisible majority remains undetected, following trajectories that carry them through interplanetary space without triggering the automated algorithms designed to identify unusual motion patterns. Theoretical predictions based on stellar dynamics and planetary formation efficiency suggest that next-generation surveys operating at their design sensitivity limits could detect several interstellar visitors each month, providing unprecedented insights into the compositions and origins of debris ejected from planetary systems throughout our local galactic neighborhood. These observations will reveal whether the handful of confirmed detections represent typical examples of interstellar debris or unusual objects that happen to develop conspicuous signatures during their passage through our solar system. The continuous expansion of survey capabilities creates an accelerating pace of discovery that challenges conventional assumptions about the rarity and significance of interstellar visitors. Only took 4 decades of dedicated asteroid surveys to realize that our solar system functions as a gravitational crossroads where debris from other worlds arrives continuously, most of it remaining invisible until chance encounters reveal its alien nature. The endless vigil continues, night after night, as humanity's electronic sentinels scan the darkness for signs of visitors from distant stars, gradually mapping the invisible traffic that flows through our cosmic neighborhood and connecting our small world to the broader community of planetary systems scattered throughout the galaxy's spiral arms. The surveys continue their silent watch as Earth turns beneath star-filled skies, carrying our small world through regions of space that have witnessed the passage of countless wanderers from distant suns. In the quiet hours before dawn, when the last telescopes complete their nightly observations and data flows through fiber optic cables to computing centers scattered across continents, the accumulated evidence settles into databases that grow larger with each passing season. Somewhere in the darkness beyond Neptune's orbit, objects too small and cold for detection drift inward on trajectories that began their journey millions of years ago, around stars whose names appear in no human catalogue. These silent messengers carry within their frozen nuclei the chemical memories of worlds that never formed, of planetary systems disrupted by gravitational chaos, of stellar environments where different physical laws govern the condensation of gas and dust into solid matter. The mathematics that describe their approach work with patient inevitability, calculating perihelion passages and closest approaches with precision that spans decades into the future. Some will develop faint Comet as solar radiation warms their ancient ices, betraying their presence to human observers for brief months before continuing outward into the galactic depths. Others will remain invisible until they pass close enough to Earth that radar echoes reveal their alien origins through orbital parameters that speak of interstellar journeys. The realization settles slowly across human consciousness that we inhabit a world drifting through cosmic crossroads, where materials from throughout our local galaxy converge and diverge according to gravitational choreographies that operate on scales of space and time beyond immediate comprehension. Each confirmed detection reinforces patterns that connect terrestrial existence to stellar processes occurring light years away, dissolving boundaries between local and cosmic phenomena. In the deepest sense, Earth orbits not through empty space, but through an ocean of debris whose invisible currents carry chemical information about stellar births and deaths, planetary formation and destruction, galactic dynamics, and cosmic evolution. The next visitor approaches even now, following mathematical certainties that will eventually bring exotic materials formed around another sun into contact with the gravity well, where human civilization developed its capacity to recognize messengers from distant worlds. The vigil continues, patient and methodical, as automated systems scan the darkness for signs of the next arrival, the next glimpse into cosmic processes that operate far beyond our solar system's boundaries. Only sleep now, as the endless watch proceeds through cycles of observation and discovery that reveal our planet's place within a galaxy filled with wandering fragments of other worlds. The surveys will resume tomorrow night and the night after, searching the darkness for visitors that carry starlight from suns we have never seen.